the second and final of our pointer talks, we're going to have a look at some miscellaneous aspects and also delve into arrays and the linkage between arrays and pointers. As mentioned in the previous talk, pointers are rather fundamental to the execution of programs on modern computers. And we're going to see this again here, specifically when we have a look at arrays and, if you like, behind the scenes, how arrays get to be implemented. But we'll start off with some miscellaneous aspects, and here we're flagging up one of the dangers inherent to the use of pointers. And this danger here you can see in a line of code over on the left hand side. We're declaring an integer pointer, so it's a pointer variable, it points to an integer, PTR somewhere we're calling it. Now at line 1, what we will do is we will reserve and set aside, let's say it's a 32-bit system, 4 bytes of memory, which holds the address. Now normally, having created a pointer variable, we then assign it to a particular address. We say, okay, here's the thing you're pointing to. Now, that's what we should do. In this example, we've omitted that stage. We've forgotten to do it. So in line 2, we say that, okay, go to our pointer variable, look at the thing that it points to, and then change that value to 0. The problem we have with this is that we don't know where those 4 bytes of memory that we've allocated, where they actually point to. All we've done is we've reserved 4 bytes of memory. Now those 4 bytes are likely to contain some values. Who knows what they are? These were things that we were creating, for example, on the stack. Then depending on what we previously had on the stack, this may then be the content of that particular pointer variable. Nonetheless, we're going to that particular address, and we're then changing the value to, in this case, 0. And that really is just corrupting memory. If you put this in, now you wouldn't put it in directly like this, but basically it simulates or emulates the condition where you declare a pointer variable, but for whatever reason it isn't actually assigned, or you forget to do the assignment, and it can be sometimes easy to do this if you have a large complex piece of code with different pointer variables within that. But this results in a program that is fundamentally dangerous. Maybe 9 times out of 10 you will run it and nothing overly bad will happen, but that 10th time the bytes that you've reserved may point to something important, may point to the executable code, and you end up changing that and effectively crashing the program. So that can be one source of problem where, you know, every once in a while your program just randomly crashes. Very difficult to find those types of debugs. So it's important, if using pointers, to make sure that we always assign them to a particular address. Other miscellaneous aspect here ties into what's known as the arrow operator. This is quite a convenience that was put in for the use of pointers. So we can see an example over here where we have defining a struct called rec. So let's say a rectangle or whatever. And within that struct we have, in this case, only one value, but we could have a number of values. And you can see in the box to the right of that 3 different ways then we can access the val variable defined within our rec struct. First of all, at line 1 we are actually declaring, in this case, a rec, a struct itself, on, let's say, stack or wherever it is. I'm then doing rec.val is equal to 20. So we're accessing the val member variable within our rec struct, and we're setting it to value of 20. And that's the normal use case. And line 4, here we are creating a new rec. We're using the new keyword. So this is something that will be allocated on the heap. So a chunk of memory will be set aside on the heap for storage of this particular structure. And we get back a pointer, the address on the heap that we have been allocated for this particular rec structure. So we get a rec star rec pointer out. Now in line 5, this is perfectly valid, looks a little bit cumbersome. Here I'm using my dereferencing operator. So I'm doing asterisk PTRX, so I am accessing the thing that I'm pointing to, which is my rec structure in the first place. Then doing .val, so I'm saying here it is a structure, I want to access the val variable within that structure. So it's perfectly valid, we'll compile, just looks a little bit cumbersome. In line 7 and line 8, we have equivalent code. So line 7, we're creating or allocating a new rec on the heap, same as before. In line 8, we're using the arrow operator. So arrow operator, 2 characters, sort of the hyphen and the greater than symbol, and they're doing ptrrec val. And that means go to the thing that you are pointing to, and then access in this case, the val member of it. And we're assigning equal to value of 20. So it's cleaner, it's a little bit easier to understand what is being entailed there, even though functionally is exactly the same. Pointers, and this ties into one of the powerful aspects of pointers. Pointers have numerical values. They refer to an address in memory, but it's not 100% accurate to think of them as integers. If we think back to when we introduced a data type, we said that a data type has a defined range of valid values. So 4 is a valid integer. 4 is also a valid memory location. -2 is a valid integer. It isn't a valid memory location. Importantly, we also said that a data type, other than having valid values, also has a list of permissible operations. So we can divide one integer by another integer. But it doesn't make any sense to divide one pointer by another pointer. So don't think of pointers as integers. They are numeric, but they are different. Now, this said, there is actually a list of mathematical operators that you can apply to pointers. I can take a pointer and I can add a value to it. I can subtract a value from it. And that does get into the question then of what happens if you subtract a value and you get a negative address. I can also decrement a pointer, same as sort of adding or taking away 1. And I can also compare 2 pointers. I can ask if one pointer is the same or less than or greater than the other one, and that'll look at the address they point to and then perform that comparison based on those addresses. Being able to change the value of a pointer, being able to add or take away from it, is actually a very powerful capability of a pointer. And there's an important aside about this here, that if we have a look at the fragment of code at the top, you can see here we got we're declaring a new. Let's assume that we have an array already created somewhere in memory, and we are pointing or ptrint, integer pointer, to the address of the first element within that particular array. So ptrint contains the address of the start of that array. In line 2, we're doing ptrint plus is equal to 3. Now, there's a couple of different interpretations of this here. So we are increasing our integer pointer. It doesn't increase that value by 3 memory locations. So if we were pointing to memory address, say 1000 in hexadecimal, it doesn't change it to 1003. Instead, the interpretation of this is that it increases my integer pointer by 3 integers. It steps forward 3 times the size of an integer in terms of the memory address. So assuming a 4-byte integer, we would end up then in memory address 1012. So that's an important characteristic. When we add or subtract or increment or decrement our pointer variables, we are stepping them forward or backwards by chunks of memory, and those chunks are sized by the thing that it points to. This is a good thing because it makes it much easier then to manipulate a pointer and step onto, if you like, the next thing or the previous thing if we have an array of these different pointers. We'll see that when we sort of look at arrays. But at the bottom ties into some of the common forms that you might see used when people are using pointers. They're sort of quite common aspects here. So asterisk PTR val plus plus is quite a common one. This case we got the dereferencing operator, pointer to variable. So there we use the value or access the value of the thing that we point to. And we have a post increment, the plus plus occurring after it. Having used the thing that we point to, we increment our pointer. We go on to the next thing in memory after whatever it is we have used. We have a post increment in the line 2. So in this case, we've got a pointer to, let's say, an array. We go on to the next location within this array. So that's our pre-increment. Our pre-increment first of all, and then we do our dereferencing and we access the value of that location in memory. In line 3, we are using the value, we're accessing the value we point to in memory, and we then got a post decrement. So we then change to the value before that, for example, within our array. And in line 4, we've got a pre-increment. We change to the previous value in the array first of all, and then access it and use it. So there are quite compact ways of accessing a value within an array and then stepping on to the next one. Obviously, if we are able to change and to manipulate pointers and add or subtract values to them, we are jumping through memory. C++, as we said, it assumes that we know what we're doing. So it doesn't use array or range checking on this. So if I accidentally leave the bounds of an array, I overshoot the end or I jump before the start of it, C++ isn't going to care. It's going to assume, well, you must have done that with a reason. So we have to always be careful when we're using pointer arithmetic within arrays to make sure that we write our algorithms in a manner that means we cannot leave the array. If we do, we'll be accessing the memory of something else, and that is going to cause problems. Let's now finally have an explore of pointers and arrays and to see, if you like, the commonality between the two of them. So if we have a big array, let's say in this case 10,000 integers, and I want to access the 5,341th element within that particular array. So I've got a small challenge about, well, how do I work out and get access to that particular address? How do I access it? Now, obviously, what you don't have is a lookup table which says that, okay, if you're interested in this particular value, here's the address that you go to, because it doesn't actually help doing that. Instead, what happens behind the scenes is that a calculation is performed. And this calculation works because we can assume that this data is stored in a contiguous chunk of memory. So what happens behind the scenes then is that we go to the address in memory of the start of the array, and we increase this by the index times the size of each element in terms of bytes. And that will give us a new address, and after that calculation, the address will be the address in memory of the element that we were interested in. So you can see an example down at the bottom where if we had index of 3, so we're accessing the sort of index 3 within our array, we would go to the start, we would then add on to that our index 3 times the size of, in this case for example, an integer, and we would then jump forward to the location of the element 3 within that particular array. So a small calculation gives us a means of jumping to a location within memory. And you can see fundamentally from this perspective here that this is pointer manipulation. We are using a pointer to the start of the array and then stepping it forward by a certain number of elements. Doing this, it means that if we want to access and to manipulate values within an array, you can do it using the normal array notation, we can do it using pointer notation, and generally there's always a one-to-one correspondence between these two things. So in line 1, here we're declaring an array of data size 10. In line 2, here we're declaring a pointer to the start, or to the address in memory of the start of that array. So basically data and pointer to data, referring to the same chunk in memory. In line 4, we are going to an ith element. We're assuming i's 0 up to 9. We haven't had something beyond it, and we are taking out whatever value we have stored and storing it within val I. In line 5, we are doing something that is utterly equivalent. It will take out and store exactly the same value. In this case, we are saying PTR data points to the start of the array. We're performing some pointer arithmetic. We're adding on I, and effectively that will step forward I elements along that array, and we're then dereferencing it, so we're accessing the value stored at that location. So line 4 and line 5, they are equivalent. There's no difference between the two. There is a danger within this, and you can see it here, that in line, this is the fragment code at the bottom, in line 1, we're declaring an integer. So it's just a single int, not an array, and we are then getting a pointer variable that points to the address in memory of this particular integer. So we declare the integer, and we have another pointer variable which points to the address in memory of that integer. Line 2 is valid. It will compile, it will execute, but it is silly. So effectively, we are going to that address in memory, and we are stepping forward by 3 integers worth, and we're then accessing that value. Now, the reality is we don't have a clue what on earth we are pointing to. It's not an integer array, it's just an integer, so we're accessing some data beyond this. Doesn't work. Well, who knows what's going to happen. It's a mad thing to do. In line 3, this is also valid. It will run, it will compile, it will also probably crash your program as well eventually. So there we're doing ptr int and in brackets 3. Now, this is exactly the same notation that we would use whenever we access an array. And this gets into the idea that if you have a pointer to an address in memory, you can add on and use your normal array notation. And the fundamental observation about this then is that under the scenes, the compiler is happy to interpret a pointer as an array and an array as a pointer. So it doesn't really make any distinction between the two. And anytime we add on our array offset, basically it's interpreted as a form of pointer arithmetic. So in the implementation of C++, and indeed most other languages, that arrays and pointers, they're basically the same thing, that you can more or less use them interchangeably. Certainly within C++, other languages you can't. There'll be much more type checking. So all arrays effectively are simply forms of pointer manipulation. The converse doesn't hold though, because sometimes pointers don't always point obviously within an array. It may point to a single element, so a degree of caution is deserved. The const keyword also ties into pointers as well. So for const, it's a way of us as a programmer indicating that something can't be changed. And there's 3 different types of application of const. So your default pointer is a non-constant pointer to non-constant data. So what that means is that the thing that I point to, I can point to different things. So this non-constant pointer, I'm allowed to change the location I point to. If it's non-constant data, it means that I'm allowed to change the contents of the things that I point to, and that's your default option. The other 3, and we'll look at these next slide, so non-constant pointer to constant data, constant pointer to non-constant data, and constant pointer to constant data. So let's have a look at those now. Non-constant pointer to constant data is the first one. And you can see the implementation here. We've got int data is equal to 10. Then in line 2, we've got const int star pointer data is equal to location of data. So in this case, the value that PTR data points to is considered to be constant. We're not allowed to change that value, though we can't change the location we do point to. It's basically a read-only pointer. Now the original data, it may not be constant, but we're basically saying for this pointer, you can point wherever you want, but you're only allowed to read the things that you're pointing to. Here we have a constant pointer to non-constant data, and if you look at the declaration at line 2, you can see that the const has changed its position. So before the int, after the int star, after the pointer definition. And that's the way that C++ has to interpret what it is you mean that is constant. So in this case, that the actual pointer must always point to this particular location in memory. It can't change the address that it points to, and hence presumably the thing that it points to. But you're allowed to change the value of the thing that you point to. And finally, looks a little bit ugly. Look at line 2, const int star const PTR data. In this case, we must always point to the same address in memory, and we're only allowed to read from that particular address in memory. So constant pointer to constant data. Why do we have these? It ties into a remarkably important principle. It's a principle of least privilege. And this is a good programming one for all languages. It says that if you are declaring a function or some piece of functionality, you only want to give that function, that piece of functionality, sufficient access to whatever it is, to the data, that it needs to do what it does, but nothing more than that. So you do not give a function more access or more privilege than it needs to do its job. Sufficient amount, and then that's that. And const is a way of doing this. So it means that if you have a function that accepts a pointer, but you do not envisage that pointer will ever change the thing that it points to, then you declare it as a const pointer. If you accept a pointer and you only want to read the value of the thing you accept in, then make it a const val pointer as well. This helps by way of producing safer functions. It also means that if you are calling the function and you're taking in a const pointer, you can pass in, it will accept a const pointer, it will accept a non-const pointer. It gives you a little bit more flexibility as to what you can pass in to it. Pointers, their memory addresses, you can, under a number of cases, recast a pointer. And by recasting a pointer, we are reinterpreting what it is that the pointer points to. And here we're going to use static cast, sort of the recommended C++ 11 way of doing that. Now, static cast, it is a compile time cast, and so it happens at compile time, and there the compiler will say, okay, can I safely reinterpret this pointer as pointing to a different thing in memory? So assuming we had a circle shape class, you can see them here, and assuming they're linked via inheritance. So circle is a type of shape. So then at line 1, we're declaring a new circle on the heap. We get a pointer to that. In line 2, we are declaring a pointer to a shape, and we're doing a static cast to a shape from our existing pointer to a circle. And at compile time, then the compiler will check to see, okay, circles can be turned into shapes. I can do that. So it is a valid compile time cast. But at line 3, I try to cast it into an integer, and it's unlikely there isn't going to be a way of turning a circle into an integer. So in this case, the compiler won't find any way of validly doing that. In that case, it won't compile. It's an invalid cast. A dynamic cast is one that is performed at runtime, not at compile time. It is a runtime check. So if you have to check up and down within an inheritance hierarchy, so I have a pointer to a shape, but I want to say actually that is a pointer to a circle, then a dynamic cast is a runtime cast that will check to see is that the case, is that going to be a valid conversion to perform. Now, this is actually a nice distinction between the C++ mecs. That static cast, you know when it will be checked, when, if you like, the cost of doing that will be fulfilled at compile time. Dynamic cast will have a performance impact because it is a runtime check. So at least C++ makes it explicit as to when these things are tested. You can also have pointers to functions. So functions are simple instructions within memory. So instructions will have a location within memory, and the set of instructions associated with a particular method will store within a certain location within memory. So if I wanted to, I can have a pointer to a function. And you see a definition at the bottom where we have a pointer to a function. It returns a char star. This particular function accepts in an int, a char star, and an int. And where we normally would have the function name, here we have a pointer to a function. So basically, this is a pointer that points to an address in memory that contains executable code that expects an int, a char star, and an int, and will return a char star back out. It means then that if you have this, you can pass your pointer, your function pointer, in as an argument to a method. And this is quite good for some methods where you want to be able to say, okay, for example, sorting. Here's a function you should call that is able to sort whatever data it is that has been processed at this point in time. So function pointers, somewhat niche, but also quite powerful as well. Smart pointers then. This is one of the last things we want to have a look up in this one. Raw pointers, as mentioned, are just locations within memory. Smart pointers, now these are what Java, what C# has, what C++11 recommends that you use. They are more than just simple locations in memory. Generally, they offer additional functionality. And the type of functionality they can offer is that whenever they go out of scope, whenever they're deleted, so for example freed up from the heap or the stack, then they trigger some action. And most often the action they trigger is that the thing that they point to, they delete that as well, or they tell the thing to delete itself. So they are a good way of preventing memory leaks from happening. So smart pointers, basically they're classes within C++. So that they're written in C++. You can override different operators. So they override the dereferencing, the arrow operator. So they have the appearance of working in the same way that pointers do, but behind the scenes it's really a class that has a range of methods that does this additional safety checks. C++, there's two standard smart pointers available within the library, and again in Java and C#, you just have references and it's managed automatically behind the scene. Here C++ exposes a little bit more detail about it. You've got a unique pointer. So this is a pointer that only points to a single object, and that's the only thing that points to that object. So whenever the pointer goes out of scope, you automatically then can delete the object. And you have a share pointer, which is what we have in Java and C#, but there's a bit more overhead involved with this, it's a bit more flexible. In this case, you can have multiple pointers pointing to the same data in memory. And effectively, if you delete one pointer but there's another thing that still points to it, nothing happens. It's only when the last pointer to it gets to be deleted that the thing that it points to is also deleted along with that. I'm going to end up looking at references. Reference, now you have them in Java and C#. In fact, reference values are basically what we use in Java and C#. We get a reference to a particular instance of an object. You also have references within C++, and you can see one declared over in line 2. So in line 1 we're declaring an integer. In line 2 we're declaring a reference to that integer using the ampersand operator. And anytime you create a reference, you must, at the point of definition, define what it is you are referring to. You can't have it sort of hanging about not referring to something. It must always refer to something. What's the difference between a reference and a pointer? A reference, you can think of it as a named constant for a given address. So more or less a non-null const pointer. It must always point to something. It is not allowed to be null. It is not allowed to change the thing that it points to. Nice thing about references is that they're automatically dereferenced. So effectively, they are a pointer to something, but you can just use the name of the reference, and the compiler will automatically dereference it. You don't need to say that that is going to be the case. References, pointers, really the same thing in terms of how they work under the scene. References, if you can use them, are generally a better thing to use. They give you cleaner looking code. They're also somewhat safer because you can't have null references. You can't forget to dereference them. So where possible, favour the use of references if you do need to have effectively a pointer to something, but you're not going to change the thing that you point to as a constant pointer, but maybe you're going to change the value of the location that you're pointing to. So summary, it's the same one as before, but there's a little bit of additional meat now by way of what we have a look at. So pointers are actually very powerful. They're very flexible. They give us a way of identifying different locations, of controlling the access to those locations. If we're allowed to change what we're pointing to, allowed to change the value of the thing we're pointing to. We need to be careful when using them to make sure that we do not inadvertently access or change the wrong type of data, or access data in different ways.